Hello everyone, I'm Chen. A doctoral candidate from Harvard Institute of Technology in China. It's my pleasure to share the research with you. The topic of this report is Morphology design of university campus for energy saving based on multi-objective optimization in cold region in China, which is divided into the following four parts. Climate of North England area between 40 to 45 degrees. North latitudes in China is cold with long winter. The average temperature in January reaches 15 to 30 centigrade below zero. It has a heating period of nearly half a year, so energy saving design of buildings has become an important issue. Earlier studies have been done on energy utilization and saving of university campus based on regional climate, and this paper focused on the conceptual design stage of campus buildings in cold regions of China. In order to improve the energy saving performance of buildings in winter, it is necessary to minimize the heat dissipation and maximize the passive utilization of solar radiation, which forms a problem of multi-objectives optimization. According to the related research, the overall optimization can be achieved through the evaluating each objective. So the Pareto theory was used to solve this problem, which is a powerful tool to evaluate different optimization objectives, and the Pareto optimal solution set can be achieved. The study consists of 4 steps, including the morphological survey and prototypes, evaluation index of energy saving, and parametric program, and the multi-objective optimization calculation. The first 10 university campuses in northeast of China were selected and surveyed through the setback map, and the prototypes of campus building were extracted. The range of building parameters, including the length and the width of the building outline, the height and the depth, were summarized, and then 4 prototypes were obtained, which are the centralized, L-type, semi-enclosed, and enclosed. Secondly, as to reduce the heat dissipation of building volume in winter, the Sheep coefficient was selected as the first objective in this study, which can be calculated by the surface area and the volume of building. At the same time, the solar radiation received on the building surface during the heating period in winter was taken as a second objective, which can be obtained by simulation. The parametric program was constructed to calculate the evaluation index of different prototypes. It was established by the Grasshopper on the Rhino 6 platform, so that the morphology of building prototypes and optimization objectives calculation can be linked and evaluated constantly. The fourth part, the Octopus toolset, was used to load the evolutionary algorithm to realize the automatic generation of the prototype and optimization of the 2 objectives. The setting is shown in the table. After the 26 generations of calculation, the objectives of Sheep coefficient and the solar radiation had achieved significant optimal results, and over 200 sets of Pareto optimal solutions were obtained. Each point in the figure represents a case of prototype. The closer the point located to the coordinate origin, the better the energy saving performance was. It can be seen that the objective values distribution was different according to the 4 prototypes. And the distribution of morphological parameters corresponding to the optimal solution is different for the 4 prototypes. The first part is the conclusion. From the table, it shows that the centralized have an advantage in shape coefficient, while both centralized and L-type building have more advantage in solar radiation utilization. As for the optimal morphology parameters, the table shows that for the wide scale, 4 prototypes all have flexible range and can achieve better energy-saving performance with a scale of 30 to 90 meters. For the length value, types of semi-enclosed and enclosed were more compatible for the length scale larger than 60 meters. For the building height, the distribution of 4 types was relatively similar, among which the enclosed type is more flexible for the building type of less than 40 meters. In terms of the depth scale, the centralized layout varied widely, and the depth scale of the other 3 types were mainly concentrated between 17 to 22 meters. And above is a brief report of my research. Thank you for listening.